Okay, so welcome back. Tueshe kuka live in wa Greenwell. Kuesha komandini fintu ifi. All right, so we can start. So there was the introductory part that was done, the introduction to chemical kinetics, and you guys should have learned about the general rate. Okay, general rate, it was the relationship between reactants and products. Reactants are going to have a negative, products are going to have a positive. Then the balancing numbers are going to have an inverse relationship, and so on. That was the general rate. Then we went to the rate law. Okay, so the rate law just focuses on reactants. But even though it just focuses on reactants, the rate law does not have a negative in front. Okay, then the rate law is going to have a rate constant K. The rate law is going to have each reactant raised to a particular power. Okay, and the powers are referred to as the orders of those things. So at least you should have that introductory part. Chi, hello. Yeah, so we're just talking about what the previous video talked about, so that even as we start, we all start on the same page, so that no one is behind. Okay, so this is hopefully going to be a very brief session. Okay, so we're going to talk about the Arrhenius equation. Okay, but the correct way of reading this I had is Arrhenius. Anyway, Arrhenius equation. Then we're going to talk about the integrated rate laws. So there's zero order, there's first order, there's second order. But one of those that I've seen to be most important is the first order integrated rate law. Yeah, okay, so just focus on the main things so that we don't waste time. So let's focus on the relevant stuff. Okay, so I think we're going to start with the Arrhenius equation. Okay, we can start. So the Arrhenius equation. So the Arrhenius equation plays out like this. We get K is equal to A e to the power negative EA over RT. Okay, so it's important for you to know this equation and how to derive quite a number of things from this equation. Okay, because this might be required when it comes to solving for activation energy and the like. Okay, so K is the rate constant. Okay, this is also basically just another constant, Arrhenius constant. This is an exponent, so this is a base of E. Base E, you remember, natural logs, whatever. Yeah, this is temperature in Kelvin. This is R. Now, this R, when we're talking about energy, should have units that have joules. What are the two values of R that you can remember, the gas constants? What are the two values of R that you remember from the gas constants? Universal gas constants. What are the two values of R? You remember he was 82 in 06, blah, 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 blah. What are the two values of R? What are the two values of R? Okay, then E is the activation energy. Activation energy. Okay, so one value is 0.08206. You left a 0 there. Yeah, 0.8206. So we have 0.08206 8206. And then the other one is going to be, who can remember the other value of R? Anyone to remember? Oh, a bright future value incarnation at Arrhenius. Okay, interesting. The other value of R is going to be 8.314. Now, units of the one on top is going to be liter atmosphere per Kelvin mole. Units for the one below is going to be joules per Kelvin mole. Which one do you think is appropriate? Where this expression involves activation energy, and energy, you guys know, is measured in joules. So which of these two is the most appropriate? The one on top or the one below? Which of these two constants is most appropriate for use in this equation? Because we have energy is measured in joules. So which of these two is the most appropriate to use? Which of these two? So the one below, yes, because the one below has joules. So this energy is measured in joules, so the one below should have joules. Okay, makes sense. So we have K is equal to A e to the power negative EA over RT. Okay, you don't really need to concern yourself with A. You're going to see there's a derivation we're going to do and A disappears. Okay, A includes collision frequency, what, it's some funny thing. But don't concern yourself with A, you see how it will disappear. The first derivation, I have something that has a base of E. And this whole thing is actually an exponent. How can I bring this exponent down? What do you think I should introduce? How can I bring this exponent down? What is the only mathematical concept that allows us to bring exponents down to make them coefficients? Okay, so we're going to introduce ln on both sides. Excellent. The natural logarithm. Okay, so I'm going to introduce ln on both sides. Okay, so we're going to have ln k is equal to ln a, okay, e to the power negative ea over rt. Okay, now you guys know that when you're multiplying logs, it's as good as adding them, because this a is multiplying with this thing. Okay, so this can be written as ln k is equal to, so ln k is equal to ln a, okay, plus ln e to the power negative ea over rt. Actually, I should have put this in brackets. So the ln is for everything. And because these two things are multiplying each other, they're going to split up. And you guys know that when you multiply things and you have a log, it's as good as adding them. Okay. So I've written ln a and then ln e to the power whatever. Okay. Then this is going to come in front. I'm going to have ln k is equal to ln a. Okay. This is going to come in front. I'm going to have negative EA over RT ln E. Now, what is ln E? If you guys can remember your logarithms. As silly as all these questions appear, you guys are actually revising logs if you don't know. What is ln E? ln E is log base E of E. What is ln E? I think we've done such quite a number of times. What is ln E? Okay, so ln E is 1. ln E is 1. Good. So this is going to give us ln k is equal to ln A minus EA over RT. Okay. This is better written as, anyway, you can write it like this, but I prefer to write it like this. ln k is equal to negative EA over RT, okay, plus ln A. So this is the other form of the Arrhenius equation. Okay, so we've converted it from its exponential form to its logarithmic form. Okay, now the applications for these for your syllabus are very, very, very low. Okay, the application of the Arrhenius equation comes in when you are trying to compare two experiments. So, what if you have two experiments? What if you have two experiments? What if you have two experiments? Okay, so it's the same reaction, but you do it under different conditions. Okay, so this is going to be experiment 1. This is going to be experiment 2. So for experiment 1, we're going to use the same Arrhenius equation, except experiment 1 is going to have its own constant, okay? And experiment 1 is going to have its own temperature. Activation energy is the same regardless of the conditions, okay? So experiment 1 will have its own constant, experiment 1 will have its own temperature. E is the same, R is a constant, it's the same, A is the same, it doesn't change, okay? So for experiment 1, this is going to be written as ln K1, just to show that we're talking about experiment 1, is equal to negative EA over R. So E and R are the same throughout. The only thing that will differ is T. So we need to say T1. Okay. Plus ln A. So this is the equation, writing it in the form that shows that this is for experiment 1. For experiment 2, this is going to become ln K2 is equal to negative EA over RT2, okay, plus ln A. Now, I want you guys to look at both equations. What is common about both equations? Like, what part is appearing in both equations? Is it the lnKs? Is it the EAs? Is it the lnA? What part is appearing for both equations? What part is appearing in both equations? Like exactly, no change. What part is appearing in both? What part is appearing in both? Quickly comment. So lnA appears to be present in both of these, okay? So make lnA the subject. So for both of these, I'm going to make lnA the subject of the formula. This is going to become ln K1. This is negative. When it crosses, it's going to become positive. So this is going to become plus EA over RT1, okay, is equal to lnA. I've made lnA the subject of the formula this side. Let me make lnA the subject this side. I'm going to get ln K2 plus EA over RT2 is equal to lnA. I've made lnA the subject of the formula. I hope you guys remember the transitive rule, okay? This is equated to lnA, and this whole expression is equated to lnA. lnA is the same as lnA, okay? Yeah, so if this whole thing is equated to lnA, and this whole thing is equated to lnA, then I can equate these parts directly to each other. You get? Remember I told you you don't really need to concern yourself with A, because it disappears when we derive. So because of the transitive rule, lnA, I can equate these other parts to each other. So I'm going to get ln K1 plus EA over RT1, okay, is equal to ln K2 plus EA over RT2. You see that? Now, I would like to put like terms together, okay, sort of. So I want the constants to be on one side of the equal sign, and I want anything that has t to be on one side of the equal sign. You get? Now, what units do you think t has What units do you think T has? What units do you think T has if R has units of joules K more? What units do you think the temperature has? What do you think are the units for the temperature? What do you think? I want you guys to be engaged in this lesson so that you don't forget. Okay, so T is going to have units of Kelvin. Excellent. So I want things that have ln K to be on one side. So this is going to come this side, and this is going to come this side. Okay, so I'm going to write this ln K will not move. So this is going to be ln K1. This ln K was positive. When it crosses over, it's going to become negative. So negative ln K2, okay, is equal to, this EA is positive, so I'll write it first, the one that has T2. This is going to be EA over RT2. This EA, the one that has T1, is positive. When it crosses over, it's going to become negative. So minus EA over RT1. I hope you've seen this. So this has become negative on this side. This has become negative on this side. Now, I want us to focus on this part. Subtracting logs is as good as doing what? When you subtract logs, it's as good as doing what? When you subtract logs, it's as good as doing what? We use the principle somewhere to say, okay, multiplication is as good as this. Now, what of subtracting logs? This is as good as what? Ababa lembati 273.15. Twaisho no kwisho bati ka girlfriends tabakwata. All right, so subtracting logs is as good as dividing them. So this is as good as ln K1 will be on top. So the one that's first is one that will be on top, divided by K2, okay, is equal to, notice that EA is the same, R is the same. You get? So I can factor out EA. I can have EA over R, okay, and then I'm going to be left with 1 over T2 minus 1 over T1. You can leave it like this, or you can simplify it further, like you can find the lowest common denominator, blah, 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 blah. But if you can reach this stage, then you are okay. Okay, so let's quickly do an exam question. Let's quickly do an exam question that requires the use of this formula. Yeah. So question. 2 experiments were conducted, okay, for the same reaction. Okay, so meaning products, reactants are the same. Okay. The data below was collected. Okay, so this is temperature in degrees Celsius, and then this is the constant, and units are going to be s to the power -1. So temperature for the first one, they found the temperature to be 189.7 degrees Celsius. For the second one, they found the temperature to be 251.2 degrees Celsius. We don't need to include degrees Celsius because they've told us that everything below here has degrees Celsius. Then the first constant is found to be 2.52 times 10 to the power -5. Second constant is found to be 3.16 times 10 to the power -3. Okay. Then they ask us to say, calculate the activation energy for the reaction. Okay, you guys remember what activation energy is? This is, can you be asked to derive? I'm not too sure. Yeah, but what about me, Peter? Show that ln k over 1 is equal to EA over R, open brackets, 1 over T2 minus 1 over T1, and so you may be asked. So just quickly go through the derivation process. I don't think it will take you a lot of time. Just write the Arrhenius equation for K1 and for K2. You get? And then equate everything to ln A, make ln A the subject. And then use the transitive rule and equate them to each other. Easy stuff, no thinking. So equate EA for the reaction. Pointers. Now, if you look at this question, what problem can you see? What is the first problem that you can see? There's something that we've been given that can't go directly into the Arrhenius equation. Okay? By the way, we are comparing two reactions. So we'll use the form that has K1 and K2. You understand? What problem can you already see from this data that has been given? Temperature. Aye, temperature ya pakafi. So this temperature is in degrees Celsius. We need to convert it to Kelvin. So next, convert temperature to Kelvin by adding 273.15. If you are sonta. All right, by adding 273.15. So this temperature, T1, I'm going to call this as my first temperature. T1 is going to be 189.7 plus 273.15. T2 is going to be 251.2 plus 273.15. Okay, where is my calculator? Okay, so this is going to be 189.7 plus 273.15. So this gives us 462.85 Kelvin. Next, 251.2 plus 273.15. So this gives us 524.35 Kelvin. Okay, 0.35 Kelvin. Then we plug into the formula. So the formula is ln K1 over K2, okay, is equal to EA over R, open brackets, 1 over T2 minus 1 over T1. Okay, we just plug in. All they want us to find is EA. And then one other thing, what did we say the value of R is? For those who can remember, what did we say the value of R is? Remember there are two values of R, so choose the correct one. There are two values of R, so choose the correct one. There are two values of R, so choose the correct one. What is the correct value of R to use in this equation? What is the correct value of R? Okay, good. 8.314. No need of including units. T1 is going to be 462.85. Okay. T2 is going to be 524.35. Yeah, we plugged in. And then K1, we've been given K1. K1 is the first constant on top. This is going to be a K1. So K1 is 2.52 times 10 to the power negative 5. So K1, 2.52 times 10 to the power negative 5. K2 is going to be 3.16 times 10 to the power negative 3. Okay, so we plug all this in and we do our calculation. So don't be intimidated by these things. Hey, Arrhenius, jazz. She do know this is done. So let's go. So this is going to give us ln, open brackets, 2.52 times 10 to the power negative 5 divided by 3.16 times 10 to the power negative 3, okay, is equal to EA, we don't know EA, divided by R, 8.314. Open brackets. Yes, data will be provided. You'll be given what to use. Divided by, multiply by 1 over T2. T2 is 524.35 minus T1, 1 over 462.85. Okay. Easy stuff. Now, your calculators cannot handle this at a go. You need to find the lowest common denominator and the like. Mine can. So I'm going to punch everything in at a go. Okay. So this is going to be 1 divided by 524.35 minus 1 divided by 462.85. Okay. All right, so this gives me negative. So this is going to be EA over 8.314 multiplied by negative 2.55 times 10 to the power negative 4. Okay. Then this side, this is going to give us, I can plug everything in my calculator. So this is going to give us ln. So this is going to give us ln. On top, I am going to put in 2.52 times 10 to the power negative 5. 2.52 times 10 to the power negative 5, yeah. And then 3.16 times 10 to the power negative 3. Okay, this gives me a negative. And it makes sense. The negative that we got will cancel out with this other negative. So this gives me negative 4.83. Yeah, there are no exponents here. So this negative cancels out with this negative. Look, I'm looking for EA. You get? So, to simplify both sides, I can multiply everything by 8.314. This is now algebra, so the order doesn't really matter. Okay, so this times that is going to give me 8.314 times 4.83. So this is going to give us 40. So 40.16 is equal to EA. Now, this 8.314 will cancel out with this 8.314. So I'll just be left with 2.55 times 10 to the power negative 4 EA. This is just algebra. I'm trying to make EA the subject of a formula, so I'll divide both sides by 2.55 times 10 to the power negative 4, 2.55 times 10 to the power negative 4. So that cancels out. So EA is equal to, so activation energy is going to be 40.16 divided by 2.55 times 10 to the power negative 4. Easy stuff. So that is 157,490.2. What do you think are the units for EA? What do you think are the units for EA? What are the units for EA? What are the units for EA? What are the units for EA? Okay, joules. Good, joules. And obviously, if you express this in kilojoules, it's even going to be a smaller number. So if you express it in kilojoules, the point is going to move 3 times. So this is as good as 1.57.5 kilojoules. This is the same. I hope it makes sense. So just remember Arrhenius equation. Don't worry about the Ka, it disappears. Know the equation that can compare 2 reactions. Okay. Know how to derive it. We went through that process. So this is not as hard. Okay. We can now move to the next part. Integrated rate laws. integrated rate laws. Okay, integrated rate laws. So it's the same. So let me just quickly run through. We have the general rates, then we have the rate law, and then we have integrated rate laws. Now, integrated rate laws, the only one that has shown to be relevant is the first order. At least learn the first order, then we can go to other orders. You get? So first order is priority, understand the first order, know it, and then we can learn the other orders. Okay? Because most questions that come through require you to use data from first order integrated rate law. So this law is, so you just need to learn it the way that it is. And you don't need to learn how to derive this integrated rate law. It is derived using integration and the like, blah, blah, blah. But you don't need to worry about that. So this is going to be ln, open brackets, at is equal to negative kt plus ln a naught. Okay. This is the equation. My advice is write it a second time so that you get a because memes. Okay. This is concentration. This is the final concentration. This is the initial concentration. This is the rate constant. Okay, and then K obviously refers to time. Time in seconds. So that is the first order integrated rate law. Okay. Now, half-life. Half-life of a first order reaction. Half-life. Half-life refers to time. Half-life is actually a type of time. Half-life refers to how long it would take a 10 kg bag of sugar to become 5 kg because someone is miangling. How long would it take a 10 kg bag of sugar to become 5 kg if someone is miangling it? Okay, so half-life basically refers to the time it takes the initial concentration to become half of what it originally was. Okay, so I won't just give you the equation for half-life. I'll also show you how to derive it, so at worst case scenario, if you forget, you can still put 2 and 2 together and remember it. So half-life, remember the integrated rate law. The integrated rate law for a first order reaction is going to be ln at is equal to negative kt plus ln a0 or a naught. Now, for us, okay, if my initial is going to be 2, what do you think my final should be for me to be talking about half-life? If my initial concentration is 2, what should my final be for me to be talking about half-life? If my initial is 2, what should my final be for me to say, okay, I'm talking about half-life now? According to this definition. So if my initial is 2, my final should be 1. Okay, so your final should always be half of what you started with. So if I start with 4, my final should be 2. If I start with 3, my final should be 1.5. If I start with 7, my final should be 3.5. Okay, so if I start with 2, my final is going to be 1. Good. So this is going to be 1. And then t is going to have a different symbol. Anyway, I'll change that later. So I'm going to substitute these things into the expression. Okay. So the rate law is ln at is equal to negative kt plus ln a0. So I'm trying to derive an equation for half-life. So half-life is a time, okay? So I'm basically just going to try and make t the subject of the formula. So let me make t the subject of the formula, and then I make substitutions later. Okay? Or I can actually substitute now. We said at, a0 is going to be 2, and then at is going to be 1. So I substitute. This is going to be ln, at is going to be 1. At is going to be 1, okay? Is equal to negative kt. Now, to show that I'm dealing with half-life, I'm going to put a subscript of 1 over 2 where I have the t, plus ln a0, that is going to be ln 2. Okay, then I'll put things that have ln on one side. So this is going to give us ln 1. This ln will cross over to give us minus ln 2, okay, is equal to negative kt half. Okay. Now, when you are subtracting logs, we discussed it's as good as dividing. So this is as good as ln 1 over 2 is equal to negative kt 1 over 2. Okay. So even if you had chosen your initial to be 10, your final would have been 5. You'd have ended up with 5 over 10, which is as good as 1 over 2. So it's always half here, regardless of what concentrations you use. So 1 over 2 is as good as 0.5. This becomes ln 0.5 is equal to negative kt 1 over 2. Now we can plug in ln 0.5 in our calculator. So you guys should know this is 0.693. So ln 0.5. So ln 0.5 is negative 0.693. So negative 0.693. The negative is important because it will cancel out with this other one. Is equal to negative kt half. Then I need to make t half the subject of a formula. The negative will cancel out. I'll be left with 0.693 is equal to kt half. So I'll divide both sides by k by k. So the equation for half-life of a first order reaction is going to be t half is equal to 0.693 divided by k. Okay. So how do questions come? They'll tell you for a first order reaction, k is maybe 0.2 per second. Okay, what is the half-life? Yeah. So they've given you the constant, and whenever you see them just give you the constant, know it is a first order reaction, because it is only a first order reaction that is 0.693 over k, like in terms of the half-life. Easy stuff. So just plug in. In this case, this would be t half is equal to 0.693 divided by what? 0.2. And whatever you get is your half-life. That's basically about half-life. So the next time we find time, we are going to do a full question where we get to derive the order, okay? And then we also get to do other calculations involving integrated rate laws and the like. They tell you to say, okay, the final is 84%, what? Yeah, so for now, you have the introduction to chemical kinetics. If you've studied, hopefully we have rectified some things. If you haven't yet, at least this introduction is going to be a huge step in the right direction. Okay guys, today has been a very, very productive, tiring, yes, and busy day, but at least we've gotten one or two things done. Okay, so please revise. For those that need guidance regarding what to revise, please start studying chemical equilibrium. Study chemical equilibrium part 1, part 2, part 3, especially Le Chatelier's principle. Okay, understand what QC is, understand what KC is, the relationship between QC, or rather between KC and P and KP, understand how to calculate delta N, understand what happens when you flip a reaction, and so on. So please study chemical equilibrium. Understand it very, very well. Because when I teach chemical equilibrium, I'm going to be very fast, because I'll be rushing to go to acids, bases, and salts. So for you to understand acids, bases, and salts, you need to have had a very, 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 very good understanding of chemical equilibrium. Don't look down on each topic. Understand chemical equilibrium. All right, have a very good night. Take care until we meet again. Bye-bye.